guys, let's talk about what we discussed so far. That general slicing technique. But if your solid ends up being the solid of a revolution, instead of a revolution, I think I misspoke with an indefinite article. I meant, if your object is really a solid of revolution, then you and I have discussed both the disk and the washer method. What I want to do next is talk about what I refer to as the cylindrical shell. And I can spell cylindrical. I really can. This is just a really pretty way of computing volumes of solids for revolution. Not that it's more advantageous in general over the washer or disk method, but sometimes it is. Sometimes it's not. Sometimes you on your own need to make a decision on what technique is more appropriate. Before I take a peek at an example, I want you guys allow me just to play with pretty pictures. Excuse me. My goodness. Here is the x-axis. Here is the y-axis. Suppose I got some funky looking curve that does this. Y equals fx. And I want to restrict my tension to the interval from A to B. And look at the region bounded by that graph of the x-axis, only that region of it. Now, if I were to revolve that about the horizontal x, I misspoke, sorry. If I were to revolve that about the vertical y-axis, wouldn't that give me an image in 3 space that kind of looks like this?
You're going to need a hole in the top, right?
Yeah, I'll just submit the boundaries up top. And again, you've got to forgive me for my drawing. Bottom line. I think that what I'm doing is revolve my region about the vertical y-axis, but I'm doing it in a very different fashion than I did last time in class with that washer method. In this case, it would be the washer method. So you guys watch me for a minute. Let me subdivide the interval from A to B into I'm not going to finish my sentence. You've heard this too many times. In your deep, deep REM sleep, you finish my sentence. I'm going to subdivide the interval from A to B into n subintervals with equal length. It'll be a regular partition. And over the, which interval do I want to look at?
A to B?
The ith subinterval. The ith subinterval. In other words, from x sub I minus 1 to x sub I, I'll choose an arbitrary value of x, so let me call it x sub I with a bar over it. I'll go up to my curve, and I see a point x sub I, comma, f of x sub I with a bar over it, and I'm getting too sloppy. Hold on. I said it correctly, I'm just being too sloppy with my pen. I said the point x sub I bar, comma, f of x sub I bar. But I will use that y coordinate to determine the height of this approximating rectangle. But instead of computing the area of that rectangle, I'm going to take that rectangle and rotate it about the x-axis. And if I do, I think I get something that looks like this.
The x-axis or the y?
Did I say the x-axis? I'm so sorry. I'll be careful. I said let's take that vertical red rectangle and rotate it, I should have said, about the vertical y-axis. And if I do, I think I get this. Which everybody's clearly a cylindrical shell. And by the way, the vertical height of the shell is what? Y sub I, or x, f of x sub I with a bar over it. I think its thickness is 1. Change in x. And everybody, if I took some tin snips and cut it right in the middle and try to pry this apart, wouldn't that kind of make it look like this? And if I continue to pull it apart, would the shape look more like this? And if I pounded it flat with a hammer, would it look like this? Use high school geometry language. kind of geometric figure is that in free space?
Rectangle.
A rectangle. Actually, a rectangular solid. And the way when I compute the volume of a rectangular solid is we merely look at its length and its width and its height. Oh shoot! In this case, actually, its height would be f of x of I. Its thickness will be. But I think its length, this right here, in terms of my original picture, is going to be. Yeah, the circumference of the circle, which is 2 times pi times the radius of the circle, but jeepers, the radius of the circle is nothing more than x of I with a bar over it. So now if I were to compute the volume of the solid of revolution, I think I'd be taking the limit as that increases without bound. That's how many subdivisions I have from A to B. Of the Riemann sum, of those beasts over there, but I think as in terms of the integral, that's going to end up being nothing more than 2 times pi times the radius times the height times the thickness as x ranges from A to B. I can just as easily rotate an object about the horizontal x-axis using the cylindrical shell method, just as easily, and my formula or my integral ends up being 2 times pi times the integral from C to D of a y times f of y, and I'm going to integrate back to y. If I'm revolving about the x-axis, not the vertical y-axis. But jeepers, you guys, this is just a pretty picture from basic geometry. So putting this to practice. Starts so slow. Okay, everybody, I'm doing another poor job at asking this question. Here's the question. Consider the region bounded by the Grasslow's equations. Take that 2-dimensional region, revolve about the y-axis, and compute its volume. Well, I think the first thing I need to do is draw a pretty picture. Here's my x-axis. Here's my y-axis. I think this will be my parabola, a portion of my hyperbola. And I'll stop at x equals 2, and y equals 0. I think this is the region I generate. Now, if I'm going to take this 2-dimensional region, revolve it about the vertical y-axis, I want a yes or no answer. Isn't life a 100% absolute piece of cake using the Washer method? I'll ask that again. Is my life an absolute piece of cake using the Washer method?
No.
What do you know? Why not?
The Washer method, no, because it's not going to work. There's
Well,
no space between the y-axis and the start of the graph.
I think there is for any y that is not equal to 0.
it'd just be a lot longer.
Yeah, I think it'd be a little bit longer. Maybe not a lot longer, but I'd have to split up as 2 different integrals, wouldn't I?
Yeah.
Because I think my outermost radius is going to change at that last top right corner point. Will you buy that? So if you guys don't mind, can I use this as a catalyst to guide this new technique? I will use this example to compute that same darn volume. I'm just going to use this new technique called the cylindrical shell method.
Is there a certain point in time when you could always use one over the washer?
Wow, what a good question. To be honest with you, depending which technique you use, you get a different integrand. And one technique might generate an integrand with which you cannot evaluate the integral. It might generate an integral, if I can speak more correctly with my English. You might generate an integral with one technique or the other that for you at this stage of the game is non-integrable, or for everybody is non-integrable. I have to use an approximation technique.
Would you specify which one you want to use? Or?
What a good question. Sometimes I do and sometimes I don't. Sometimes I like to not specify because sometimes you generate an integral you cannot evaluate. And I want you to see that. So the answer is, I'll do both. Or I can do both.
Sounds true.
So everybody, let's use the cylindrical shell method. Actually, I take that back. Can I stop for a minute? Can we just talk about these points of intersection? Are they easy? Are they easy? Yeah. 2 comma 0. I agree. Now, if I'm going to use the cylindrical shell method, then I think I'm going to consider a vertical sliver. And I'm going to take the sliver and revolve it about the vertical y-axis to create a cylindrical shell. And I think I can label a point at the very top. Call it, how about x sub I bar, comma y sub I bar? Would you guys agree? Set up an integral that determines the volume of the solid revolution is simply going to be an integral with 2 pi pulled out front. And I'm going to be integrating with respect to the variable y. And listen to what I talk about everything in between. What's that? How do you know that? Yeah, you guys, I think I'm completely wrong again. You take a picture, take a peek at my picture. I think that vertical rectangle is vertical, is indeed vertical, and I think its horizontal width is going to be a small change in the x direction, which is going to turn into a dx, not a dy, when I take the limit of a Riemann sum. Do you see my point? However, if I were to compute the volume of the solid revolution using the washer method, don't you guys agree I really would have a dy, not a dx, if I were to use a washer method? Because those would be horizontal slivers, wouldn't they? Yes?
In that case, would you be subtracting 2 from the actual equation?
You mean to generate those radii? Yeah, I think it'd be a bit more work. Now, don't take it the wrong way. I still think in this example, using my new cylindrical shell method, I still might have 2 integrals. I just think it would be so much easier to write. All right, here we go. I think the vertical height that rectangle right here is going to be nothing more than f evaluated x. It's going to be my y sub i's. And I think the radius of the cylindrical shell is going to be nothing more than that x coordinate. And I'm going to be integrating from 0 to 2. It's just that, albeit rather unfortunate, my function f changes its output when x is on either side of positive 1. So I think when I integrate from 0 to 1, my f of x is going to have an output that looks like this. However, when I actually integrate from 1 to 2, my f of x has a different output, specifically this. So I think in the end, I merely have 2 pi times the integral from 0 to 1 of x cubed with respect to x. Now, carefully listen to what I say. Don't look at what I write. Plus, from 1 to 2, is that just simply 1? Or shall I say, I got 2 pi times, is that x to the 4th over 4 from 0 to 1? Plus, is that just simply an x from 1 to 2? Oh, you guys, this is just arithmetic at this point. Is that 2 pi times 1/4? Plus 1. So 5 has pi. That's what volume of the solid revolution in terms of cubic units. You guys, is that okay so far? If it is, can I rewrite the question? Number 2. Now, you guys, in my picture, I know I'm going to be a tad bit off scale. I just don't care. Here's the x-axis. Here's a line. X equals 5. Now, if I just concentrate on the one vertical sliver and revolve just it, not the entire thing, about the line x equals 5, take a peek what it looks like. I think with my red pen, my vertical sliver rotated about that line becomes something like this over here. And here's going to be my cylinder. And let's just talk. To set up my integral, I think the volume's gonna be computed by looking at 2 times pi, times the integral from A to B. Oh, how about just 0 to 1 this time? Let's just cut to the chase. Of the radius, times the height, which by the way doesn't change, is still x squared, and I'm gonna integrate with respect to x. Plus 2 times pi times the integral from 1 to 2 of the radius times the height, and I'm going to integrate with respect to x. But now I need to take a break. We need to come in and talk about just how we're going to identify the radius of that cylindrical shell. So humor me. With my green pen, somebody help me with this. What's this position on the horizontal x-axis? X of I bar. What's this position on the horizontal x-axis?
X equals 5.
Oh, sorry, I was going to say 2. You're right, it is positive 5. Would you guys not agree for that ice cylindrical shell, this is going to be the radius of my ice shell? Now, I want to press upon you how lazy I am. Watch. If this really is a radius in green, then I think since I'm living on the x-axis, it's going to be represented by the big X value minus the small x value, which is clearly just simply 5 minus x of I bar. I think that's going to be another name for my r sub I I'm writing backwards. For my r sub I. And so I think in both these cases, the radii of the cylindrical shells are going to be 5 minus x. Did you see it?
The book does it a little differently.
I know it does. That's what I'm saying. Can you see what I'm doing in my picture?
I can see what you're doing, but wouldn't the book do it x minus 5?
Definitely not.
No?
As a matter of fact, if you chose x minus 5 in my picture, that would mean that all your radii are going to be negative. I think, Bradley, I'm just a little bit different because I'm so lazy. I say, plant your right foot at the large x value, and your left foot at the small x value, and look at the difference of large minus small.
Okay.
Can you guys allow me? By the way, sorry, I'm stumbling. Can I not finish? I mean, that's easy, isn't it? Okay. I got 2 minutes for the break. Can I do this? But that'll be over here. That means I get to erase. By the way, that means with my red pen, I get to rotate. And in rotating, don't I get something that kind of looks like this? Humor me. How do these 4 numbers change? They don't. How do these heights change?
They don't.
They don't. I think the only thing that's going to change is what you see in green. So let's just talk about what we see in green. And I think in green, then this should be considered right here, the radius of an ice sliver. But if that's the case, then let me mark clearly what this position is on the x-axis, just x by bar. And I think this position right here on the x-axis is just fixed at -1. And so for this ice cylindrical shell, I think the radius is nothing more than the large x value, which I called x by bar, minus the small x value, which no matter where this vertical sliver is always equal to -1. And so I think in this example, this modified example number 1, which is now number 3, I think the radii end up being x plus 1 when I take the limit of the 3 multiples. Bradley, you don't like this.
So why wouldn't it be -1 plus x at that point?
All right, let's do it your way.
Well, I'm just wondering.
Would you not agree that rotating about the y-axis,
Yeah.
I get a certain radius, which is x of I,
Okay.
with a bar. But the radius here is going to be bigger. Well, you just said the radius of the bigger one is x minus 1. You said -1 plus x would be the same thing.
Yeah.
Then I think your radius is going to be smaller than what we had before, just rotating about the y-axis. I want a bigger one. But again,
Okay.
I'm trying to press upon you. Oh, I'm so lazy. I'm just looking at the big x value minus the small x value, and that'll give me the radius. And so I subtracted my -1 for that reason.
Okay.
I'm completely shutting my mind down. I'm not thinking at all.
I just think of it as a distance in general. 'Cause the
Yeah.
distance-
That's fine. As long as when you think of the distance, make sure you're giving it a positive connotation. Big X value minus small x value. That's all I care about. Anybody else? Sir?
What if you're rotating about, like a line that's in your graph? Like, it's in your shaded region.
What a good question. I think that becomes ambiguous, because think about it. If I were to rotate about the line x equals 1/2, am I not duplicating some of the volume?
Yeah.
And so I think it would be a very misformed question.
Well, in this case, you just have like half of it. If it was
Well,
cut right down the center.
I'm truly nervous. I think x equals 1/2 of wherever it is. Revolving, I'm spanning out some space and free space twice.
Yeah.
And so I think it would be an ill-posed question. I think it would be a silly question.
So just to be clear, the cylindrical shell method is an alternative to the washer method, or it's used for a different type of problem?
It's an alternative to the washer method, but I have to confess, sometimes the cylindrical shell technique will give you a nasty integral you cannot evaluate, and sometimes the washer technique will give you an integral you can't evaluate. Or maybe sometimes both techniques apply, but one's a heck of a lot easier to actually evaluate than the other.
So they pretty much do the same thing.
They better give you the same value as long as both those techniques give you an integral integral. And I know in the past I've written some Math 31 exams where I say, do it both ways, and you better come with the same answer.
Are there things we should look for that would, like lead us in one direction or the other?
Yeah, sometimes you can just take a glance at the region you're revolving about an axis or a line and say, well, it splits up into two integrals, but my other technique doesn't. So I'll choose the one technique that does not split up my image into two integrals when I compute the volume of the solid revolution. Outside of that, then I think it comes down to this. Set it up, see if you can integrate the integral. If you can't, bag it, go to the other technique. Happy? Guys, can we take our 10 minutes? I